All right, thank you very much. Today I'm going to talk about our work on understanding some nonlinear random matrix models that arise in estimation and learning. I understand my audience comes from diverse mathematical backgrounds, so I'm going to start by having a quick overview of some classical random matrix ensembles. So throughout this talk, we're going to organize our data in terms of matrix with n columns. And we should think about all these columns as independent samples, some from some underlying probability distributions in RD. Now, once you have this data matrix, you can compute the sample covariance matrix H, or equivalently the Gram matrix E. It is very well known that the empirical distribution of eigenvalues of H would converge as the problem dimensions D and N both grow, and under very mild conditions on the underlying probability distribution P of X, to some well-defined limiting distributions known as Marchenko-Parser distribution. In this plot, the blue bars are the empirical histogram of the eigenvalues of H, and the red line is the Marchenko-Parser distribution, okay, the limit. And the actual form of the limit will depend on, of course, the aspect ratio of D and N, and also will depend on the correlation structure of the underlying probability distribution. This is a classical result. A classical reference is at a level of global law is given by Silverstein Bai. And later on, this convergence in the sense of local law was first studied by Oders and HDL and co-authors, right? So for this, yes. Yes, great.
What distribution do you sample from, correct?
So very general. So for example, the typical assumption is you have distributions that are factorized or centered, but you don't need to have these kind of independent core structures. No, they're not. So the actual limiting distribution depends on the population covariance matrix. And then sometime in the literature, people call it a deformed Marchenko-Parser distribution, but these are just Marchenko-Parser distribution. If you look at the original paper of Marchenko-Parser, they already studied the general covariance structure. Okay. All right. But in this talk, we're going to consider nonlinear models of random matrices, and there are a few examples. The most familiar example is kernel method. So in this case, this is going to be an n by n matrix, where n is the number of data vectors, and ij's entry of this kernel matrix is the result of applying a nonlinear function sigma to the squared L2 distance between the ith and j's data vector. Okay, you can also run into nonlinear random matrices when you study multi-layer neural networks, and here W1, W2, W3 are the weight matrices, and X is the input data matrix, and sigma is the entry-wise activation function. And typically at initialization, the weight matrices are randomized. They are randomly initialized, with, for example, with independent Gaussian entries. Then you are dealing with a nonlinear random matrix. If you look at this attention module, which is a key component of the transformer architecture, and here X is the token matrix, and W is a combination of the key and query matrix. So essentially what you are dealing with is a weighted Gram matrix, followed by a nonlinear operation, which is a softmax. There are several other examples. For example, in robust statistics, you want to do a shrinkage of covariance matrices, or you want to do a nonlinear factor model. You want to factorize a matrix into two low-rank components, but you have additional nonlinear observation channel before you can do the factorization. Okay, so this type of nonlinear random matrices was first studied in this paper by Al-Karoui for kernel matrices. And the setting is you start with a Gram matrix, H, that is a pairwise inner product of data vectors, and you apply an entry-wise nonlinearity. Okay. Now, the typical scaling of random matrix is such that all the entries of H of order 1 over square root of n. Okay, if you have done random matrix, you will know that this is the scaling that would make the most sense. But if this is the scaling that you apply, and then you are going to apply sigma, a function, to H, then you are essentially only looking at the behavior of this function around 0, because all these entries are very small, n is large. Then the obvious idea is to do Taylor series expansion. That means every entry of this matrix can be expanded up to the second order. And the high order term, you can show that they are negligible in the sense that the matrix associated with the high order terms has diminishing operator norm. So you can safely ignore the high order terms. And then the second order term, that is not centered, but after centering, meaning after removing the expectation, you can also show that this matrix, if you run indices I and j, this matrix would have a diminishing operator norm. So in some sense, the main technical part of Al-Khoury's paper is just to show that by using moment method, this part has a diminishing operator norm. Okay, but then once you have ignored the last two terms, what you are left with are the mean part, which is a constant matrix, plus a linear part. Okay, I'd like to call this regime a simple regime of nonlinear random matrices because that is actually not linear, not nonlinear. Essentially, you are dealing with a linear function. You only need to do a Taylor expansion around sigma. In some sense, this is not so exciting, but a more interesting or more challenging regime is the case when you first scale the entries of the matrix to be order 1 before applying this nonlinear function. So in this case, of course, you are fully experiencing the entire nonlinearity of sigma, and this more challenging regime was first studied in this paper by Chen and Singer for kernel random matrices, and there is also a related line of work studying rectangular versions of these matrices in the context of random neural networks. Okay, so underlying all of these papers, and in many cases implicitly, there's actually an equivalence principle that is fairly general. So I'm going to highlight this equivalence principle. Essentially, the equivalence principle says that a nonlinear model, in many cases, is asymptotically equivalent to a linear model plus noise. To be specific, suppose you study a kernel matrix under this more challenging scaling, then you can show under certain conditions that the model A is asymptotically equivalent to another model B, which is another matrix of same size. But B is defined as a linear combination of 3 components. Mu0, mu1, mu2 are scalar constant, and 1 is an all-1 matrix. X times X transpose, that is a linear part. So this is the first 2 components are the same as what you would get from Taylor series expansion. But unlike the previous simpler regime, the high-order term has to be captured by an independent noise matrix. So there is additional noise matrix that you cannot ignore and in this setting. So in this talk, I'm going to try to explain this kind of equivalence principle in the example of a kernel random matrices in polynomial scaling regimes. And the underlying idea turns out to be linearization via polynomial chaos. So we're going to introduce what is a polynomial chaos and what is the idea of this kind of equivalence. And the second part, I'm going to show as an application of this kind of a mathematical understanding of how do we understand so-called in-context learning by a linear attention module. Okay? So there are 2 parts. The first part is more about mathematical structure. Okay. So I'm going to start with the first part. This is joint work with colleagues here at Harvard, Sophia, Ben McKenna, who is now at Georgia Tech, H.T. Yao, and my former student Hong Hu, and my collaborators at Yale and Google. Okay. So the first part, we're going to start with an experiment. So the experiment is the following. We want to learn a function that is defined on a d-dimensional hypersphere, given a set of n training samples. Each piece of training sample is a combination of input x of I, which is a vector sampled uniformly from the d-dimensional sphere, and output y, which is the function value at x of I. Okay, I have a total of n such input and output pairs. And I want to learn this function using a very simple algorithm, which is kernel-ridge regression. I don't want to go to the details, but essentially it's just about solving a least square problem involving a kernel random matrix. Okay, if you do this experiment, then this is the learning curves that you would get. And here, the horizontal axis is log n over log of d. D is the dimension of the underlying sphere, and n is the number of samples that you get. So from left to right, you are taking more and more training samples. And the vertical axis is the test error. Okay, the lower the better. So clearly there is a staircase phenomena before 1. And because the horizontal axis is in log n over log d, before 1, you are taking sublinear number of samples. N is sublinear in D. And then there is one type of plateaued error. And then once you cross one, go to 1 and 2, essentially N is superlinear in D, but subquadratic in D. Then you have a lower plateau, and so on and so forth. Okay? Essentially, what happens is that in each phase, you are only learning a part of the function. And for functions defined on the hypersphere, you can have a very natural orthonormal basis known as a spherical harmonic basis. And then what happens is in each phase, you're learning spherical harmonic components of the function of different degrees. Okay, so I'm going to talk about a little bit more detail later on. But then this horizontal axis is log n over log d. That is actually looking at the problem at a very coarse scale, because around 1, in a very small neighborhood around 1, n can vary a lot. So if we zoom in into these transition regions, for example, in the first transition point 1, let's look at n over d as this ratio, n over d, and then there are different behaviors. If we zoom in these kind of curve, the test error has well-defined limit, and there are even multiple descent behaviors if you are looking at the quadratic scaling and cubic scaling and so on and so forth. Okay, and this is the motivation. And also, so Blake here. So Blake, in his PhD, did a lot of early works about this kernel type of rich regression problems. Okay, and we want to understand the underlying mathematical structure of why. How do we characterize this kind of kernel rich regression? Okay. So the setting. This is the motivation for studying this kind of kernel random matrix in this polynomial scaling region, where the number of training samples can scale as the dimension d to the power of an integer. And the classical high-dimensional statistics consider the case where L is equal to 1, but we consider a general polynomial scaling, because if you look at different polynomial scales, there can be very interesting and different behavior. Okay. All right, and before I show you the result, let me first introduce this family of orthogonal polynomials called Hermite polynomials, and these are the first 4 Hermite polynomials. And then what we need to know is that these polynomials are orthogonal polynomials with respect to the standard Gaussian measure. Okay, and they also form a complete orthonormal family. So if you can continue. So that means any reasonable function, meaning square integral function sigma of x, and sigma is going to be our kernel function, can always be written as an infinite linear combination of these Hermite polynomials at different orders. Okay? This is a one-dimensional function. Now let's look at a kernel matrix. That is a matrix A applying sigma, a function, nonlinear function, to pairwise inner product. Now, because sigma can be written as a linear combination of Hermite polynomials entry-wise, and because sigma is applying to this inner product entry-wise, we can write the entire matrix A as a linear combination of these so-called Hermite matrices, where each Hermite matrix, for example, H of K, is just a special case of A where instead of a sigma, apply a polynomial, H of K, the kth Hermite polynomial to the pairwise inner product. So the entire kernel matrix is a linear combination of these polynomial matrices. I also want to emphasize that this is not a matrix polynomial. This is entry-wise polynomial. That is different. If you apply matrix polynomial, that's much simpler. All right. So what is the main result? In this paper with my colleague HDL, what we established is this general equivalence principle. The setting is we study this kind of a random kernel, inner product kernel matrix under this kind of polynomial scaling where n scales as a constant alpha times d to the power of L, where L is any positive integer. And then we first expand A as an infinite linear combination of these Hermite polynomials. And then what we showed is the following equivalence principle. When D is large, then we can say the first few components, in this case, first L components are low-rank components that can be ignored. And H of L, the L plus 1th component, will be asymptotically equivalent to a Wishart matrix whose distribution is given by the Marchenko-Parser distribution. Okay? And what about a higher order component, h of L plus 1, h of L plus 2, and so on and so forth? What we show that these higher order components are asymptotically equivalent to Gaussian orthogonal matrices, meaning that they are equivalent to independent symmetric matrices with independent Gaussian entries. So their spectrum densities would converge to semicircle distributions. Moreover, asymptotically, all these higher order components can be treated as if they were independent. So essentially, you are dealing with a case where you have an independent summation of a Wishart matrix and a collection of GOE matrices. And because these are all GOE, they can be combined into a single one. So for people who have worked on random matrices, then you will know that A, of course, is not of this case, but the equivalent model that we can establish can be very easily studied through, for example, free convolution and so on. So these are very standard type of ensembles. Okay, and this type of result generalizes Chen and Singer's original paper, who studied the case of L equal to 1, the linear scaling case. And also in this follow-up paper, we considered more general assumptions of underlying distributions from which we sample our data vectors. Okay, so I'm going to talk a little bit about this afterwards. Right. Okay. So what I want to do next is to spend some time on the blackboard to show what is the underlying mechanism. Why do we have this kind of equivalence? Heuristically, why should we believe there is this kind of equivalence, meaning that the HL, the Lth Hermite polynomial is equivalent to a Wishart matrix with Marchenko distribution law, and all the higher order components are essentially can be treated as independent Gaussian matrices with semicircle distributions. All right. So what is underlying mechanism? And just to remind you, each Hermite matrix is applying a given polynomial to the pairwise inner product. And polynomial for k greater than 1, these are nonlinear functions. Okay.